Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 30. We were talking about two different cases where in one case we had a predominant thermal resistance given by the solidified metal, and in the case previous to that there was a problem related to the wetting of the surface, because of which there was a thin film which was the interfacial, which offered the interfacial thermal resistance which was predominant in nature. So, in the case where there was a predominance of the solidified metal, or this portion was predominated with a constant casting surface temperature, meaning thereby that this mold was a thin mold, and then we would like to water cool or something so that it is like a great heat sink, and so this surface temperature would become more or less constant because of that process. So, in this particular case we already calculated that the term zeta times of zeta square x error function of zeta was made equal to theta f minus theta s by root pi Cs by L from the previous derivation that we had made, and this value zeta e to the power of zeta square error function zeta had to be calculated iteratively from various values of zeta, where the right and left side would be equal to each other. So, basically corresponding to different zetas there would be standard tables called error function tables, something like what you can see here. So, you have the x value here and you have the error function of x here. So, corresponding to a certain x value, the error function is defined in this particular entries here on the column corresponding to error function of x. And so, the idea is that the zeta e to the power of zeta square error function zeta, whatever be that we had to plot with respect to zeta value, okay, in a graph, and various values could be obtained of the zeta corresponding to which the error functions are defined here, and from this graph we would like to see where along this graph exactly the right hand side of this particular equation theta f minus theta s by root pi times of Cs by L would be matching, and that would be the corresponding zeta value, and from that you could easily find out what is the time of solidification by the formulation h square by 16 zeta square alpha s, and this was in the case of predominantly the solidifying material or metal to be the most important component defining the thermal resistance. The other case that we would like to illustrate here with predominant resistance in mold and solidified metal would be the case where obviously we assume a copper mold which is a highly conducting mold with respect to the metal that it is basically solidifying. It is quite thick vis-a-vis the thin mold that we had illustrated earlier, and it is not water cooled. So, therefore, there is going to be a gradient of temperature from the mold surface all the way to the outer surface of the mold, and let us consider these temperatures to be theta s and theta 0. So, this is the only difference in this particular case vis-a-vis the case where it was a thin mold with water cooling, last case where the constant casting surface temperature was established because of that. So, in the mold metal interface the temperature theta s can no longer be assumed to remain at its initial value theta naught. So, obviously theta s will change, and theta s still assumed to be constant is decided by the thermal properties of the mold and the solidified metal, and moreover after the initial stage of solidification the interface resistance also becomes very negligible. So, we do not consider, because it is a metal to metal weld, there hardly any interfacial resistance which would happen. So, in this particular case the only significant thermal resistance is offered by the region 2 and the region 4. Okay. So, the 2 is this region and 4 is particularly this region, and the resulting temperature distribution as any instance is shown in the figure below here. So, assuming the mold to be semi infinite medium in the negative x direction. So, this mold starts from x equal to 0 at the interface or the face of the mold and all the way to the other end or the atmosphere end. So, it is the negative x direction. The temperature distribution can be again written down as theta minus theta s divided by theta 0 minus theta s equals the error function of minus x by twice root of alpha t. So, this is completely on the basis of the distribution, the solution of the one dimensional heat transport equation that we did at the first instance when we considered the temperature distribution of the sand molding. Only thing here changing is the boundary conditions and nothing else. So, this is for all the x less than 0, because obviously corresponding to x more than 0, the temperature would be higher, because the solidified metal would be at a temperature at least freezing point or higher, and the liquid is even beyond that. Okay. So, so for x less than 0, this would be the relationship that holds, and in the solidified metal, that means for corresponding to x greater than 0, the equation would change to theta minus theta s by theta infinity minus theta s. Again, this is an integration constant, just as what propped out in the earlier cases, and this actually is equal to the error function of x divided by twice root of alpha s t, where alpha s is basically the thermal diffusivity of the solidified metal. This alpha is corresponding to the alpha of the mold. Okay. So, please be very, very careful about what these metals. So, I am not going to prove the distribution function as such, because I think I have already illustrated corresponding to the sand boundaries how this function behaves. So, theta 0 obviously is the initial temperature of the mold, and theta s is the mold metal interface temperature, theta infinity is obviously the integration constant as has been defined here earlier. So, the other conditions need to be satisfied. One of them is the balance of the heat flux, at the mold metal interface, that is Ks times of del theta by del x at x equal to either 0 plus Ks basically is the thermal conductivity of the solidified metal site, okay, and that of the mold site. So, we call that K del theta by del x at x equal to 0 minus. Okay. So, the amount of heat of the solidified metal side and that of the mold side, they should be equal to each other in this particular illustration. Number 2 is that the rate of energy flow balance at the solid liquid interface, that is Ks del theta by del x at x equal to delta, which is basically at instant t. Okay. If I just look back in this figure, the metal has probably gone all the way up to delta at a certain time instance t, and it is still expanding at the rate of del theta del by or d del by dt. So, this should be equal to the amount of heat that is liberated by virtue of the solidification process, and I do not need to illustrate how we obtained this earlier, because many times earlier in other cases we have done similar manner. So, it is rho m times of L, assuming again the pouring and freezing temperatures to be same to each other. So, it is only the L factor times of d del by dt. Okay. So, having said that, now this is the second condition that has to be satisfied, that the amount of heat that is liberated from the solid, okay, this is d del, is the amount of heat that flows out into the solid metal interface, okay, solid liquid metal interface. And then obviously, the third condition that needs to be obeyed is this del T, at which the temperature should be equal to the freezing point of the material, otherwise there is no point in having the interface between solid and liquid. So, this is actually necessarily equal to theta f. So, all the above equations can be combined to give theta f minus theta s times of C s by L root pi equals zeta e to the power zeta square error function zeta in a similar manner as I had solved earlier, and also theta infinity minus theta s times of C s divided by L root pi should be equal to zeta e to the power of simple zeta square, and theta s minus theta 0 by theta infinity minus theta s comes out to be equal to k s rho m C s divided by k rho c to the power of half, which is actually equal to a constant phi as in this particular case. Okay. So, these are a result of all the manipulations of del theta by del x at x plus 0 or at x minus 0, so on and so forth. So, that all the three conditions earlier can be satisfied. Okay. And so, the three unknowns namely theta s, theta infinity and zeta can be solved from these three equations. As theta s minus theta 0 times of C s by L root pi equals zeta e to the power of zeta square phi, phi being a constant, and theta f minus theta 0 times of C s by L root pi being equal to zeta e to the power of zeta square error function of zeta plus phi. Okay. So, you can just compile all this by looking at this side here. So, obviously, we have theta infinity minus theta s being recorded here from equation 3 as theta s minus theta 0 by phi. That is exactly what we are substituting here in this particular equation, theta infinity minus theta s value, and so you are getting this first equation, okay, from the solution of this with submission of theta s minus theta infinity minus theta s, the value obtained here, okay, and the other equation here is being obtained by simply adding the phi value, okay, from this particular equation right about here to obtain so here for example we are trying to solve theta f minus theta s by L root pi C s equals xi e to the power zeta square error function of zeta. So, we already know that this theta s minus theta 0 times of C s L by root pi is actually this zeta e to the power zeta square plus phi. So, let us call this equation 1 and 2. If we add 1 to 2, so adding 1 and 2, we get theta f minus theta 0 times of CSL by root pi becomes equal to zeta I to the power of zeta square times of the error function of zeta plus phi, which is actually this particular equation is obtained here. Okay. Just adding 1 to 2. Okay. So, you find out now that in the case where the resistance comes predominantly from the solidified as well as the liquid solid the mold solid boundary, there is a slight modification to the equation that was earlier there only for the predominantly mold boundary case, okay, or sorry, solidified metal case, and in this case the only addition that has been has happened actually is to the right hand side, and this new constant phi, which is actually the ratio between the Ks rho m Cs and K rho C. Ks basically is the solidified metal's thermal conductivity, specific heat capacity of the solidified metal, and the density of the solidified metal or liquid metal, and this K rho C are those associated with the properties of the mold that is in question. So, this new phi gets added up in this expression, which would give you predominant resistance in mold as well as solidified metal. So, let us do some problem examples now. So, in one of the numerical problems, for example, here we determine the solidification time of the slab shaped casting considered in the earlier example. The casting is done in water cooled copper mold. So, basically this is the case corresponding to the constant casting surface temperature, meaning thereby that this is the case of water cooled thin copper mold, and the other one is in a thick copper mold where the predominant resistance would come from the solidified metal portion as well as the mold metal interface. Okay. In both the cases assume no resistance at the mold metal interface by means of the thin film of air or something. The mold itself is having a good joint with the metal, there is hardly any contact angle issues at the interface. So, in the following data is given for iron, the for the solid metal the specific heat capacity is 0.67 kilojoule per kg Kelvin. The thermal conductivity of the solid iron metal is about 83 watts per meter Kelvin. Theta f, the freezing temperature is 1540 degrees Celsius. L is basically the heat of solidification, latent heat of solidification is basically 272 kg per kilojoule per kg, and the density of the liquid metal or the solid metal both are about 7850 kg per meter cube for the iron metal, the solidifying metal. And for the mold side, for the copper, similar observations have been made for the thermal specific heat capacity, the density of the material, and the thermal conductivity of the material. So, having said that, let us now try to sort of maybe go ahead and solve this problem. So, in the first case, we know that when the we consider the case of thin copper mold with water cooling. Obviously, the casting surface temperature will be constant. I can say theta 0 and theta s are similar to each other. So, in that instance, if we apply the corresponding equation just as illustrated here, where this zeta I to the power of zeta square into error function of zeta becomes equal to theta f minus theta s by root of pi. So, we have theta s as the room temperature here, we assume that to be 28 degrees Celsius. The height of the casting is 0.1 meters, about 10 centimeters, that is the thickness. So, the zeta I to the power of zeta square error function of zeta becomes equal to theta f minus theta s by root of pi C S by L, where this is the specific heat capacity of the solid metal, this is the latent heat of solidification of the iron. So, we just put the values here, the freezing temperature is 1540 degrees Celsius minus 28 degrees Celsius times of 0.67, which is the specific heat capacity of the solid metal, divided by 272. These are all kilojoules. So, we do not need to illustrate this by converting into joules anymore. Okay. So, there is a kilojoule on the both the numerator and denominator. Okay. So, this becomes equal to about 2.1. So, if we really wanted to see by plotting a graph of zeta versus this term zeta e to the power of zeta square error function zeta, where these two would correspond to the whole expression here being equal to 2.1. So, corresponding to a zeta value of 0.98, which we can read from these tables as has been illustrated earlier. So, 0.98 is somewhere close to 1. So, the error function of zeta is 0.8427. So, in fact, what I am trying to say here is that 0.8427, which is the value of the error function, okay, this error function of zeta times of e to the power of zeta square. So, 0.98 square times of 0.98. Okay. So, this calculation should be equal to 2.1 or nearby. Okay. So, this is the iterative process of estimating the zeta value by again and again checking the different values of zeta corresponding to which the LHS and the right hand side of this particular equation are going to be balanced to each other. So, therefore, the zeta value corresponding to 0.98 would definitely call for the solidification time Ts now. So, for that we need to calculate what is alpha s. So, alpha s here in this case is the heat conductivity or thermal conductivity of the solid metal divided by the density of the solid or liquid metal times of the specific heat capacity Cs of the solid metal. So, this becomes equal to 83 divided by 7850 the density times of 0.67 10 to the power of 3 meter square per second. Please be very careful of the units. So, this comes out to be equal to 15.8 into 10 to the power of minus 6 meter square per second, and the solidification time therefore Ts would happen to be h square by 16 square of zeta times of alpha s. In this case it is 0.1 square meter square divided by 16 times of 0.98, that is the value of zeta square, times of 15.8 10 to the power of minus 6, and this comes out to be 0.0115 hours. Okay. So, that is how the value of Ts can be calculated in this particular case. So, as regards the estimation of the time of solidification for the second case, we will see that there is slight variation in the time of solidification. In fact, it is going to be a little more than this case, because obviously we are adding more resistance to the heat flow path by taking also the mold as a sink in the thick copper mold case. Okay. So, let us do that problem now. So, for the thick copper mold without water cooling, I would like to find out first what is going to be the phi value here. The phi is obviously ratio Ks rho m Cs by K rho C to the power of half. So, this comes out to be 83 times of 7850, the density of the liquid metal times of the specific heat capacity of the solid metal divided by 398, the conductivity, thermal conductivity of the mold times the density of the mold material times the specific heat capacity to the power of half. So, this becomes equal to 0.57, and corresponding to a theta 0 of 28 degrees Celsius, zeta times of error function zeta or e to the power of zeta square times of the error function zeta plus 0.57, which is this phi value here, should be equal to the theta freezing minus the room temperature theta 0 divided by the latent heat of solidification times of root pi times of the Cs or the specific heat capacity of the metal, the solidified metal 0.67 value. So, this becomes equal to again 2.1. Okay. And in this particular case, as if we calculate based on the iterations that we had done earlier, the equation gets balanced the left and right side corresponding to a zeta value of 0.815. So, again a graph of zeta versus zeta e to the power of zeta square times of error function zeta plus 0.57 needs to be plotted in order to ascertain which corresponding zeta would actually give you the LHS and RHS as equality. So, having said that, now therefore, with this zeta value the Ts value can be estimated as again the thickness square h square divided by 16 times of now the current zeta, which is 0.815 square times of the thermal diffusivity 15.8 10 to the power of minus 6 as calculated before, and this comes out to be 0.0165 hours. So obviously it is little more, because now you are seeing that the mold also is applying a resistance in comparison to the to the overall process. So therefore the resistance of the heat flow increases here, and it needs more time for the temperature to come to the freezing point, and therefore the time of solidification in this case is more in comparison to the other case where the the mold acts like as a heat sink, and there is a constant casting surface temperature because of that. So the surface temperature of the metal theta C or theta S, surface temperature of the metal, this can be estimated as 1540 minus 854 degrees Celsius, that is 685.4 degrees Celsius. So that is what the value would be for the surface temperature of the metal in this particular case. So obviously how we have estimated it is from the again the error function of by just calculating the theta S value, which can be done from any of these equations. The theta S, for example, in this particular case would be theta S minus theta 0 times is equal to zeta I to the power of zeta square phi times of L root pi by Cs, and theta S becomes equal to theta 0 plus zeta e to the power of zeta square phi L root pi by Cs. Okay. So that is how the 685.4 degrees can be calculated. So having said that, I think I am kind of done with now the heat transfer theory. So in summary, we have seen what happens when there is a case where the sand mold is completely the only resistive part of the to the heat transfer or the heat flow. The case 2 where there is a thin film formulated because of differences in contact angles and incomplete wettability of the liquid metal with respect to the solid surface, and case 3 again where we have considered a thin mold with water cooling, so that you have this predominant interfacial resistance vanish away, and the only resistance left in the whole picture is basically the resistance of the solid metal part. And then finally the case 4 where we assume a thick copper mold without water cooling, so that the two components, that is the mold resistance as well as the solid part solid metal resistance, both of them are of predominant nature and equal consequences. And so in this case you have also seen that the time of solidification also based on more and more resistance added to the heat flow goes higher, because now more time is needed for the temperature to equilibrate to the freezing point really of the mold surface. So having said that, I think I am done with all the heat transfer issues in casting and how to design the casting for the solidification time. So think of it now, the solidification time that you have found out by this method has to be amenable with the time scales that you have on the riser runner side, so that the idea is that a backflow can be able to sustain within this Ts time, so that the metal also does not get solidified fully, and then there is a there is also a possibility of a reverse feed, so that shrinkage etc. can be accommodated within the mold. So you will have to design from an overall sense all these problems together, considering all these different cases together for a realistic casting design. So having said that, the only other issue left in casting is the way that you place the riser, or how far you can place the riser from the mold surface, and that we are going to do in probably the next illustration or next module. Up till now, up till then, goodbye. Thank you.